A is equal to the collection of all omega such that the limit as n goes to infinity of x n of omega equals x of omega. It really is helpful to go back to first principles. What are we talking about? Why is that an event? How would you go? This is fair game on a quiz. You have to think about, what does convergence mean? Yeah. Convergence means, you give me an error bound epsilon, and eventually I'm always within that error bound.
Xn minus omega is always the probability that xn of omega minus epsilon minus the limit is less than epsilon.
Yeah, that's the kind of thing. Well, I want xn minus x greater than epsilon infinitely often. I should say I want this. That's exactly, well, I should be careful. I'm scared to say it's exactly the same. But I want this for sure. But as soon as I say all epsilon, I'm in this uncountable realm, and I can't go and play around anymore. So you have to say what you want in a countable way. So I can define, say, B for bad. I'll put a great equal to sign there since we had that before. So here I've got k equals 1, 2, 3, etc. So now I've got a countable number of events, and we know I can take unions and intersections, and it'll still be an event. And how is that related to that?
Intersection over all k.
Not
that has probability 0. The first one has probability 1.
Well, not one of them, though. I want to know, can I express A in terms of the BKs? And you almost said it. Of what? Nah.
Intersection of the union of the BK.
Nah. But this is the B stands for bad. BK is a bad thing. I don't like, but this is good. I converged. This says I didn't converge.
Compliment?
Yeah. So if you go back and look at your definition of convergence, it just means that. It means that the number of times I exceed this error is only finite for any error bound. Yeah. Okay. Yeah. No. Okay. Cool. So yes. So BK is an event, and so that means that A is as well. I know it's tedious, but there are counterexamples out there. You really have to be a little cautious. So that's something we can make sense of. The second one is really boring. There's a definition. I look at the probability of the error exceeding some value epsilon, and I want that to converge to 0 as n goes to infinity for every positive epsilon. Why would we have the two? Why would we have this and this? It's because sometimes we're too stupid to prove this. We don't ever want this, but sometimes we just can't prove our algorithm converges except in this weak sense. So that's really it. So you can cook up examples where this holds and not that, but they're contrived, you know. I mean, it's really, really rare. I can't think of examples in applications, you know, where we know that this holds but not that. Okay. Oh yeah, I forgot, I gave that away. Somebody tell me number 3, or a third one? All right. Okay, so I'm putting 4 because that's the order in the book. And so there, it just means the distributions converge. The definition is horrible. There's a definition of convergence and distribution. We want to get rid of that as fast as we can. You know, the primary definition, at least in the textbook, is that you look at the CDF, you look at the limit of the CDFs as n goes to infinity, it converges to this limiting CDF at any point where this is continuous. It's, you know, at that point. So excluding jump points, you know, of the CDF. So there are nice, it turns out, the following are equivalent. Xn goes to x in distribution. So this is commonly the way you write this. I mean, actually I should say that. Over here you'd say xn goes to x almost surely. And here you'd say xn goes to x in probability. You know, you just put a little notation there. Okay, so this is prettier. Basically, it says that a convergent distribution means that if I take any f moment, it converges where f is bound and continuous, right? But a hard thing to test because you know, test this for every single f. So there's a third. If you can just check that the characteristic functions converge for every u, then that's the same thing. And that's powerful. And it's one big application. Put a y there. You know, so going back to our CLT, it is a simple calculus exercise to prove this. You know, if you take this normalized sum and you just look at the definition of the characteristic function and do a second order Taylor series expansion, wham, you get this in a half a page. So the CLT is a really simple result. It's real. Once you have this beautiful theorem here, the CLT is up. It's a one-liner. You know. So I'm not gonna. So I think as I recall, the book has the proof, but again, you can do it all yourselves. A couple of paragraphs. You know. You use a fact that's independent, so you get the characteristic function here is a product of characteristic functions. You use the fact as 1/squared of n, which allows you to focus in on the origin. Everything gets compressed to the origin. And do a third order Taylor series expansion. The error will be 1/n to the 3 halves. It disappears. Right? All right, cool. Why do we have that? Because of that. We have this convergence of distribution is for things like this. You know, things like the CLT. What's the last one? Notion of convergence?
Mean square error.
Mean square, yeah. Convergence in mean square. So yeah, it's the only one where we have to take an expectation. So that I can kill. Okay, so basically you just look at the error, take its square, and take the expectation that should go to 0. Of course, it doesn't have to be 2. We could have had a third moment, or, you know, I mean, obviously this is just an example. And, you know, there you have it. So can anybody tell me how these guys are related? You know, what's connected to what? You know, like convergence and mean squared. Can Cool, let me see. So you said almost sure. Well, careful. Well, first of all, almost sure implies convergence and probability. Let's do that first. Because what you said is correct. And convergence and probability, it's not hard to show, implies convergence in, yeah. And then but the mean square is sort of a mystery land. So mean square implies convergence probability. Yeah. And why is that, everybody? Somebody who doesn't talk much. I'm going to call on one of you. Why does that imply convergence and probability? Come on. From the very beginning of lecture. Chebyshev. Right? So the probability that xn minus x is greater equal to c is less than or equal to the expectation so if that goes to 0, then that goes to 0. For any c positive. So this implication is just Chebyshev. But like I said, I don't know why he gets the name this limit after himself. And that's really it. But it turns out there is a counterexample. There is a converse, you know. So it's a really useful fact that convergence and probability implies convergence in mean square. It requires conditions, and those conditions are there's another random variable. So if you've got a single bounding random variable that bounds all these guys up, then you can actually go from convergence to probability, this very weak thing down here, to convergence to mean square, which looks much, much stronger, right? Yeah. But this guy's all by himself over here, all right? There's no way to go back. I mean, you go back and look at this. These guys can be all on different planets. They're not in the same world. Every random variable can be a different planet. If there's a countable number of planets, I don't know if there are. But they're not in the same probability space. There could be a different probability space for each xn. So there's no way to do it. There is something called an embedding theorem, which allows you to go backwards, where you construct a probability space that contains them all. So I'll put a little dashed line there. You know, and that can be useful, you know, that you can, in fact, I think you're going to go all the way to almost sure. You know, you construct a probability space where everything works, but it's very artificial. You know, it has its applications, but it's artificial. All right, 4:30. So, I was trying to think. I know there's more I wanted to say. And so is it obvious to all of you why this doesn't imply this? Can anybody give a condition under which this would imply this or something? You know, like what if you had a rate of convergence to 0? This goes back to the comments you made to me at the beginning of lecture. This could definitely happen. You look at the error at time n, given epsilon, and you take the sum, that turns out to be finite for every epsilon. All right? And then take epsilon equals 1 over k. Trying to remind me about my bad event over there. So bk, remember, is the probability of being bad. I'll put a so what can you tell me about bk from last lecture? Well, we know, yes, the probability of bk is 0. So that's the Borel-Cantelli lemma. All right. So if you have the probability of these primitives being finite, then the probability of the event happening infinitely often is 0, and then we know the probability of the intersection is also going to be, I mean, we know the probability of bk complement is 1. And actually, you know, I wrote A was the intersection k equals 1 to infinity of bk complement. And interesting. Interesting. Why is it obvious? I mean, I wasn't going to go this far, but now I realize that, that's a bit of a gap. If you have a collection of events and each one of them has probability 1, then their intersection is much, 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 much smaller, but it still has probability 1. And it would come from monotonicity and all that. This is something, so I think I'll stick in the homework for you. It's not trivial. You need to use the axioms of probability and the continuity theorem. But if you have a bunch of events, and every one of them has probability 1, and then you take a countable intersection, that event also has probability 1. Okay? And it's sort of, maybe it's obvious. But right now, I can't think of a 1-line proof. I can only think of a 5-line proof. All right. So if you have something, if you get something stronger here, then you can get almost sure, but something much, much stronger. So it's not going to be true in general. And it's really easy to come with counterexamples. I don't know if I should bother. Yeah, I think I should leave it to you to read, maybe. Let me see. Do I trust you all? No, I guess I will. So if you look at example 2.2 of the text, Hayek gives an example. We have convergence and probability, but not almost sure. And what he does is he takes omega fp. To be one of our favorites, omega is the unit interval. Okay, so all numbers between 0 and 1. F is the Borel sigma field. Remember, that's the smallest sigma algebra that contains all the intervals. And P is uniform. And I've got my sequence, which I can only graph. I don't know. Here's 0. Here's 1. So it's a traveling wave. So it's a skinny little wave that moves along, and when it gets to the end, it jumps to the beginning, and it reduces its width by a half and moves along, not continuously, in blocks. So Bruce actually wrote down a formula for this. I guess I'll do it. It's oh God. No, I can't. I'm just reading this. It's so long to describe. Forget it. Forget it. See the book. But anyway, so the width is like 2 to the minus k, and you move along block by block. It's just the description so long. I wasn't going to do it. And you can see if these things move along again. You have the width and you move along. If you take any point, you're gonna see 1 infinitely often. Okay, so the probability that xn equals 1 infinitely often is equal to 1, and so we do not have almost sure convergence. I mean, in fact, give me any point. Well, anyway, give me any point. You'll see I'm going to get an interval over my head infinitely often. But then if you look at the probability of, if you look at this, it's going to 0. So this, the probability of being bigger than epsilon not E. So you set this up so the width there is 2 to the minus k for some k. And so k is a function of n that blows up. And so this goes to 0. All right. Now clearly this function is not summable. You say, you see a 2 to the minus k, you think this is summable. Or something, forget it, because we know that if the error was summable, then we'd have almost zero convergence. Okay, so there's something funky going on here. But what is x? I never told you what x is. You mumbled it. Well, this what's random variable? So I've got these little xn is something that's basically 0 everywhere, except for a little interval. No. Well, its distribution is a delta function because it's identically 0, right? Because each xn is practically 0, except for it's for some little interval it's not, and so the only possible limit is 0, and so x equals 0. Yeah. All right. What else could it converge to? It's each xn, it's becoming more and more 0. So yeah. So what else what am I leaving out? I guess not. No, that's good. So I don't want to move on to anything else. That's awesome. So next lecture, I'm going to get into this geometry about relative entropy and how it leads to everything, everything you ever care about. And so go and try to look over those notes in advance. Don't try to read the whole thing, but it's the first page or two of the notes I broadcast a few hours ago. And it's an hour lecture on Thursday. We won't be able to get that far, but at least I can give you a main sort of overview of the main ideas. Good. Cool. And so office hours begins now. So I'll meander over to my office and see some of you then.